So there's any number of other algorithms here, and we'll leave in white one that we'll come back to, but let's just consider the opposite of this, if you will. If big O is our upper bound on running time, it turns out there's a vocabulary for discussing the lower bound on an algorithm's running time, which for our purposes we'll generally consider in the context of best case. So in the best case scenario, how little time might an algorithm take? Well, this is capital omega, and it's used in exactly the same way. You just say omega of n squared, or omega of n, or omega of log n. So it's the same symbology. It just refers to a lower bound. So it takes this few steps or this many steps. Big O, big omega. So what's an algorithm, therefore, that is in, so to speak, omega of 1? Like, what algorithm in the best case might actually take just one step? And who is best to answer this question today in the room, in fact? What algorithm could take one step? Yeah. Yeah, linear search could take omega of 1 steps, because in the best case, it is right there. Or in Chrissy's case, even if her algorithm is to sort of choose randomly, in the best case, it is right there, the number 50. So even her algorithm, and even our linear search algorithm, and for that matter, even our binary search algorithm, are in omega of 1, at least in the best case, because if you get lucky, you're done, one step. By contrast, what is an algorithm that takes at least n steps? So omega of n. That's a good one. So you say bubble sort, I heard. Why?
Because if they're all already in order, you just go through each comparison and then make no swaps.
Good. So in the case of bubble sort, where we generally had a lot more work to do than just finding something with a searching algorithm, bubble sort is minimally in omega of n. You need at least on the order of n steps. Maybe it's n minus 1 or n minus 2, but it's on the order of n. Why? Because only once you go through the list at least once do you know what, to be clear? That they're in order. And you know that as a side effect of having not made any swaps. So you can only determine that a list is sorted in the first place by spending at least n steps on that process. Excellent. So there's yet another one, and this is the last, whereby if you happen to have an algorithm or a scenario where the upper bound and the lower bound are the same, turns out there's a symbol for that too. You can just describe the algorithm in terms of theta notation. That just means theta of n, theta of log n, whatever it is. That just means upper bound and lower bound are one and the same. And there's more formalities to this, and you can actually dive in deeper to this in a theory class, but for our purposes, big O and omega will be a generally useful way of describing, generally speaking, just what the running time of an algorithm actually is. So big O of n squared is the fastest we've seen thus far. Unfortunately, it does actually tend to run pretty slowly. We saw it with an example of like 500 billion steps just to sort a million elements. Turns out we can do way better than that, much like in the first lecture when I crazily proposed, I think, suppose your phone book had like 4 billion pages. Well, you only need 32 steps using binary search instead of 4 billion steps using linear search. So it would be nice if after all of this discussion of algorithms and introduction of these formalities, if we can actually do better. And it turns out that we can do better, but this has been a lot to do already. So let's go ahead in here and take a 5-minute break. And when we come back, we'll blow out of the water the performance of all 3 of those algorithms we just saw. All right. So let's take a quick look at what these algorithms look like so we can actually compare them against something that I claim is actually going to end up being better. OK, so here we have an array of numbers represented as vertical bars. So small bar is small number, tall bar is big number. And so it's a nice way to visualize what otherwise is pretty low-level numbers alone. I'm going to go ahead here and make the animation pretty fast. And I'm going to go ahead here and choose, for instance, bubble sort. And actually, let me slow it down a little bit, just for the sake of discussion. So you'll see in this algorithm, bubble sort, it's making multiple passes through the list, just as I did, highlighting in pink 2 neighbors at a time and deciding whether or not to swap them, just as we were with our 8 volunteers doing the exact same thing. Of course, with this visualization, we can do it more quickly, and we can speed this up to the point where you can kind of now start to feel the bubbling effect, if you will, whereby the bigger numbers are bubbling up to the top, to the right, just as the number 8 did when we did it on paper. So this is bubble sort. And we could watch this for quite some time. And in some sense, it's kind of mesmerizing. But in another sense, it's pretty underwhelming. Because at the end of the day, all you're going to get is a bunch of bars sorted from short bars to big bars. But perhaps the takeaway is that I'd kind of have to stall here for a decent amount of time, even though we're running this at the fastest speed, because it's only fixing, at best, one number at a time, and maybe some others are improving, but we're only moving all the way to the end one number at a time, and we have to then go back and go back and go back and do more work. It's going to be very ungratifying to abort it, but let's go back to random. And now if we choose, for instance, selection sort, you'll see that the algorithm works a little differently. Let me slow it down. And what it's doing now, which is a little less obvious, is it's looking through the list for the next smallest element, and it's going to put it at the beginning of the list, all the way at the left. So it's looking and looking and looking, and it leaves highlighted in red the most recently discovered smallest element. And then as soon as it gets to the end of the list, it's going to move that smallest element all the way to the left, so that we now, kind of like the opposite of bubble sort, have all of the smallest elements to the left. Though this is arbitrary. We could bubble up the small elements by just reversing the order of our operations. We could sort from biggest to smallest. That is irrelevant. It's just by human convention, we tend to sort from smallest to biggest, at least in examples like this. And we can speed this up, but it doesn't quite have the same comparison effect, because all you're doing is a swoop through the list looking for the smallest, looking for the smallest, looking for the smallest. And so this way, it's going to kind of build up from short to tall. Let me go ahead and do it one more time, this time with insertion sort, and slow it down. And so what we're doing here is the following. We identify the next element, and then we go and insert it into the place it belongs in the quote-unquote sorted half of the list. So recall that I generally describe stuff on the left as being sorted, stuff on the right as being unsorted. And the implication of that is that even though these numbers here on the left are indeed sorted, when I encounter a new number out in the unsorted area, I might have to move some things around and shuffle things around. And unlike the cheat I was doing here in person, when I grabbed that music stand before and just kind of moved it over here, that's not really legitimate, right? This is garbage value land. Like, I should not have had access to this memory. And so what we did with our actual 8 humans was more legitimate. The fact that our volunteers did the physical labor of moving those numbers around, that was the low-level work that the computer has to do too. And you see it here all the more, either at this slow speed or the faster speed. It's being inserted into the appropriate location. So case in point, this tiny little element, we have to do a huge amount of work to find its location until finally we found it, and now we do the same thing. So all of these have some pluses and some minuses. But it turns out with merge sort, we can do even better. An algorithm that goes by the name of merge sort. But to do better, we need to have a new ingredient, or at least more formally defined, that we've kind of sort of leveraged before, but not by name. And to do this, I'm going to actually take out a little bit of code in CS50 IDE, a program called sigma0.c. And we'll see the interconnection in just a moment. So in this program, notice the following. We have a main function whose purpose in life is to get a positive integer from the user, and to pester him or her again and again and again until they cooperate and provide a positive integer. That's what the do-while loop is often useful for. And then what do we do with it? We simply pass that value n that the human typed in via getInt to a function called sigma. And sigma is like the Greek character, the capital E-looking character that generally means in math like sum a bunch of numbers, add a bunch of numbers together. So this is essentially a function called sigma whose purpose in life is to sum all of the numbers from 0 to n, or equivalently from 1 to n. So 1 plus 2 plus 3 plus 4 plus ... n, whatever n happens to be. And then via printf, we're just printing it out. So let me just run this program to make super clear what's going on. And I can do this by doing, of course, in my source3 directory for today, make sigma0, enter, /sigma0, positive integer, I will do 2. So by that definition, it should sum 0 plus 1 plus 2. So 1 plus 2, that should be 3. So I should see 3. And indeed, I see 3. Let's do one more. If I add in 3 numbers, so this should be 1 plus 2 plus 3. So that's 6 in total, and so forth. And they get pretty big pretty quickly. If I do 50, then we start to get into the thousands. So that's all it's doing. And how is it doing this? Well, we could implement this in a whole bunch of ways, but if we leverage some of our sort of techniques thus far, we might do it using a for loop. That's kind of been one of the most common tools in our toolkit. And how am I using it here? Well, I'm first declaring a variable called sum and initializing it to 0 because I've done no work yet. Then I have a for loop for I equals 1 all the way up through m. Why m? Well, just because. Recall that when you make your own function, whether in Scratch Or in C, you get to decide what to call the inputs to that function, the arguments or parameters as they're called. And just for clarity, I called it m, even though we've typically been using n. I could have called it anything I want. I just wanted to make super clear it's a different variable. But more on that in a week or so. And so I'm just counting from 1 to m, and I'm adding to sum whatever I is. Now, just as a quick check, why am I not doing sum plus plus, as I usually do in these kinds of cases? Exactly. I'm not incrementing by 1. I'm incrementing by 1, and then by 2, and then by 3, and then by 4, and so forth. So I need this loop to be counting up, and I need to be adding I to the sum, not just a plus plus in this case. Then I return the sum. And so this is an example of like an abstraction. Like I now have a function called sigma. Just like in math, you might have the big capital sigma symbol that just says add all these numbers together. I have a C function that does that. And so now higher up in my code, I can call that function and then print out the answer. But it turns out that this simple function lends itself to a nice example of another programming technique, something called recursion. And we won't have terribly many opportunities in CS50 to apply this technique, though we will towards semester's end. If you continue on to a class like CS51, you'll use it all the time. If you use another type of programming language, you'll very often use this technique. And it's called recursion. And it looks like this. Let me go ahead and open up another file that's available on the course's website called sigma1. Notice that main is identical. So main is identical, and indeed it's still calling a function called sigma and then using printf to print out the answer. So there's no difference there. But what is different in this next version is the code for sigma. So what's going on here? It still takes as input an integer called m. So that's good, because I need to know what to sum up to. It returns an integer as before. And it amazingly has like, 4 real lines of code plus some curly braces. And even those lines of code are super short. And there's no additional variables. And there's this weird, crazy logic here. But let's see what it's doing first and foremost. On line 23, I'm saying if m is less than or equal to 0, return 0. Now, why does this make sense? Well, I only want to support positive numbers or non-negative numbers from 0 to m. And so I just kind of need an error check there, right? If the human somehow passes into this function -50 or something else, I don't want the function to freak out and give unpredictable behavior. I just want it to return 0 in cases of error or when the number gets that small as to hit 0 or even lower. So this I'm going to call a base case. It's just like this sanity check, like don't let the math go beyond this point of 0 or less. So amazingly, if you really zoom in on this code, the entirety of this program really boils down to one line. And what's going on here? So I am returning from sigma an answer. But curiously, my answer is kind of defined in terms of itself, which generally is a bad idea, right? It's like in English, if you try to define a word by using the word in the definition, usually someone calls you on that, because it's not all that helpful to use a word in the definition of the word. And that's the same idea at first glance of recursion. You are using the same function to solve a problem that was supposed to be solved by that function in the first place. So what do I mean by that? Main, of course, is calling sigma. And that means this code down here that we've been looking at gets executed. So suppose that we hit this line of code. What recursion allows us to do in this case is take a bite out of the problem and then defer to someone else to figure out the rest of the problem. So what do we mean by that? Well, sigma, again, is just this process of adding up all the numbers between 0 and some number m. So 1 plus 2 plus 3 plus ... So you know what? I don't want to do all that work as I did in version 0 with my for loop. Let me just do a piece of that work. And how do I do that? Well, you know what? When you ask me, what is the sum from 0 to m? I'm going to be kind of circular about it and be like, well, it's the answer is m, the biggest number you handed me, plus the sum of everything below it. Right? So if you passed in the number 10, it's like saying, well, sigma of 10 is 10 plus sigma of 9, and like leave me alone. I don't want to do the rest of the math. But because you're calling the same function again, that's actually OK. A function can call itself. Because if you think about where the story is going, now sigma gets called in this story with sigma of 9. What does the code do? Well, sigma of 9 returns 9 plus whatever sigma of 8 is. So we're not solving the whole problem. We're handing back a 10 plus a 9, and if we keep going, plus an 8, plus a 7, plus a 6. But we're not going to do this forever. Even though I'm using sigma in my implementation of my answer, under what circumstances am I not calling sigma? if m equals 0 or is even less than 0, which shouldn't happen, but just to be sure, I made sure it can't with the less than or equal to. So eventually, you're going to ask me, what is sigma of 0? And I'm not going to be kind of difficult about it. I'm just going to say 0, and no longer do I keep passing the buck to that same function. And so even though it takes a while to get to that point in the story, because we say 10 plus sigma of 9. Sigma of 9 is 9 plus sigma of 8, which is sigma of 8, or 8 plus sigma of 7. Like it keeps going and going and going. But if you kind of mentally buffer, so to speak, much like a video in your browser, all of those numbers that you're being handed back one at a time, which are technically being added together for you by your program with the plus operator, the last number you're going to be handed back is 0. And at that point, all of the plus signs can kind of kick in and give you back whatever number you're actually looking for. So recursion is the act of a function calling itself, which is very, very, very bad unless you have a base case that ensures that eventually, as you take bites out of the problem, you will handle with a special case, so to speak, a base case, a small piece of the puzzle, and just hand back a hard-coded answer to make sure that this doesn't happen infinitely many times. So any questions on this principle of a function being able to call itself? Yeah?
So the base case here was when m equals 0?
When m equals 0 or is even less than 0, just to be sure, but yes, when m equals 0. Indeed.